Okay. Good afternoon, everyone. So I think we should start. So at the end of the last lecture, someone came to me and asked if there are any references to the computational learning theory. So actually, in this course, the course in machine learning, it partly covers the topics in learning theory, and then after that, I searched for a few more resources and supplemented here. You see the resource textbooks 5 and 6. Actually, those two links are the course websites in machine learning class in CMU and Georgia Tech. But those are mainly theoretical course, focusing on machine learning theory. And if you're interested, to know more about computational learning theory, more results, and how those results are derived, you're welcome to explore those slides, very good slides, and many problems. But in our class, because we'll mainly focus on more practical perspective of machine learning. So this is the entry level machine learning course. We won't spend too much time on learning theory. You're only required to know the key ideas, key concepts of computational learning theory, and motivation to develop machine learning theory, and how those bonds and guarantees give you the insights and guide you to choose different learning algorithms, or even for you to design new algorithms. That's our plan. So, by the way, this is the course website. Hopefully, you are not confused about the website. So it's just the course website. So it is the tab called information. Information contains all the requirements of this course in actual resources. So yeah. So if you're interested, just spend some time and viewing this website. Okay, so let's start the course content. Oh, by the way, I really appreciate that you interact with me during the lecture. And if you have any questions, do not hesitate and just ask me. But please speak loudly. It's not it's quite a big lecture room. It's not like the small room I used to teach. So if you don't speak loudly, I might misunderstand your question. Okay. So let us continue our brief introduction to the conditional learning theory. So in the last lecture, we introduced the key idea of the conditional learning theory. That is, how can we define a reasonable metric to justify or to conclude that a learning algorithm is good or satisfactory. So because the training data and the test data all sampled from some unknown data distributions, right? So there is uncertainty in the data. So we cannot expect that your learning algorithm will always 100% sure to return you an excellent hypothesis. So if you want to carry out theoretical analysis and you want to give some theoretical conclusion, it must be realistic enough such that it can give you true guidance, true help in practice, right? So that's why we introduced a concept called probably approximately correctness. So we won't say, okay, a very powerful algorithm and whatever kind of training data set can return you a very excellent approximation to the target concept, target function. That's not realistic. And instead, we think a learning algorithm or learner is satisfactory if given some small parameters, epsilon and delta, with the probability at least 1 minus delta. So delta is small, so 1 minus delta is large. So this just means with high chance. Our learning algorithm can produce a hypothesis with true error at most epsilon. Because epsilon is small, this just says that a good learner, a good learning algorithm will have a high chance to find out a hypothesis with a low generalization error. So that's the idea of the definition for PAC, right? Probably approximate correctness. So nearly all kinds of computational learning theory are studying how to quantify PAC, how to prove a learning algorithm can probably approximately correctly learn some concept and in what kind of level. So epsilon delta indicates two types of level. Epsilon indicates the level for the generalization error, right? So the smaller the epsilon, the better the learning algorithm, the better the hypothesis. Right? And delta indicates the confidence level. So the smaller the confidence, so the larger the chance, right? 1 minus delta. So you have a higher chance to get a very good hypothesis. So given the concept of PAC, right, we define PAC learnability. So PAC learnability is proposed to differentiate those easy to learn target functions and those very effective and efficient learning algorithms. Specifically, we say a concept class C is PAC learnable by some algorithm F. So remember, PAC learnability is talking about a particular type of target functions and a particular learning algorithm. If this particular type of target functions C can be PAC learnable by the algorithm L, then for arbitrary target function in this class, and for arbitrary data distribution and arbitrary setting of the epsilon delta, which correspond to the error levels and the confidence levels, our learning algorithm L can only use a polynomial number of training examples to these 4 parameters to learn a hypothesis which is probably approximately correct. So probably approximately correct is just what this sentence means. Right? So it means that, okay, with probability at least 1 minus delta, it can learn the hypothesis that has true error at most epsilon. So that's the definition of hyperlearnability. And here, polynomial means that the number of training examples required to achieve PAC should be upper bounded by some polynomial functions of 1 over epsilon, 1 over delta, number of the features. So n here indicates the dimension of feature vectors, and the size of the full hypothesis space. So hopefully you can understand this concept. So the meaning of this concept is pretty clear, and it's not very hard, but to rigorously state, to rigorously define it, is kind of tedious. So I would suggest you, if you still feel confusing, just read it for 10 times. I think you will definitely capture the meaning for this. Right. And then we can further extend hyperlearnability to the efficiently hyperlearnability. So what is efficient hyperlearnability? So if the concept C is hyperlearnable by algorithm L, and simultaneously L can produce the hypothesis with the computational cost at this time complexity also polynomial to these 4 numbers. Then we say, okay, this concept C is efficiently hyperlearnable by the algorithm L. So this directly define what kind of algorithms can you use. Right? Your time complexity cannot be too high. If time complexity is too high, it's not practical as well. Yeah, that's a good idea, and I will leave this as an exercise for you, because there will be one homework about this problem. So I don't want to disclose it right now. Any other questions? Okay, so with those basic definitions and framework, at the end of the last lecture, we were trying to justify the Occam's razor's principle. We have mentioned that Occam's razor's principle is just a guidance, or to ask you whenever you want to explain some data, explain some observations, your model should be as simple as possible. Without necessity, don't intentionally increase the model complexity. So we mentioned this is just a kind of a prevalent idea across different schools of philosophy, and this is not true. Nothing. Nothing is like a mathematical lemma or theory which you can use some induction method to prove that. But it can be justified in different ways, right? And we would like to use what we have learned from computational learning theory to give a simple justification. So to do that, we make a very simplified assumption of our supervised learning scenario. We assume our learning algorithm chooses a finite hypothesis space. Be careful, this is a finite hypothesis space. If the hypothesis space is not finite, it doesn't work. But this example is sufficient for us to illustrate our X-bit of Occam's razor's principle. And second, we assume our learning algorithm is powerful enough such that given whatever training data, our algorithm can always return a hypothesis which is consistent with all the training examples. That means the training error or empirical error is simply 0. That is our setting. That is our setting. And now, given this setting, we claim that the probability that there is a consistent hypothesis, which is consistent with all the training examples, but the true error is bigger than epsilon, this chance is less than this number, which is the size of hypothesis space times 1 minus epsilon to the number of training examples n. So basically, what does it mean? What does this claim mean? It just means that, okay, I have a good learner, right? I have a good learning algorithm. Every time I can find out a
hypothesis which returns 0 training error. That's good, right? Fit data very well. But I still have a chance to be bad in generalization performance, right? So this claim tells us that the chance that we find out a consistent hypothesis but bad in generalization performance is upper bounded by the size of the whole hypothesis space times 1 minus epsilon to m. And the proof of this claim is pretty straightforward, so I won't repeat it again. Okay, so just if you forgot it, just look at the slides. It's pretty straightforward. So now let us look into this claim. It basically says, okay, whatever strong learning algorithm you have, you always have a chance to find out a bad hypothesis. Although I can bound bad hypothesis, but in practice, I really do not want these things to happen. In other words, I want this chance to be as small as possible. And how can we do that? How can we decrease the chance that our learned hypothesis has a large true error, large generalization error? How can we do that? Increase the number of training examples, right? Why? Why when we increase the number of training examples, we can decrease the chance we end up with a bad hypothesis? Yeah, exactly right. So because this chance, the bad even that we find out a consistent hypothesis but true error is bigger than epsilon, this chance is bounded by this number. So now if and 1 minus epsilon is less than 1, right? So if you increase the number of training examples, this bound decreases, right? Meaning that it also decreases the chance of this bad even.
Does this account for overfitting? Like, as you increase the number of examples, or is that just the number of attributes?
Yeah, this of course it relates to overfitting. So we are talking everything we're talking about is the case that overfitting because the training error is 0. Right? So why we discuss this example, we want to say, okay, if my learning algorithm is so powerful that it overfits every time, and then how many training examples should I choose to decrease the bad effect of overfitting? Does it make sense? So we assume our learning algorithm is powerful, right? So every time, whatever training data you give me, I just return you a hypothesis with 0 training error. So perfect fit to the training data, right? And now I want to know what kind of chance when this overfitted model perform badly in testing future examples, right? So now we know the chance that it performs badly is upper bounded by this number. So now that we know the upper bound of this chance, we want to work on a way to decrease this chance. If we decrease this chance, we actually lower the bad influence of the overfitting. That's the motivation here. Does it make sense? So now, suppose I want to make this chance, or make this probability of bad event to be smaller than some designated level delta. What should we do? An idea? So as you guys just said, right? If we simply increase the number of training examples, obviously this bound will be decreased. And we decrease the chance, right? Decrease the chance that we end up with a bad hypothesis. Right? But now I want to quantify the number of training examples such that we ensure the chance of this bad event will be smaller than some designated level delta. How should we do that? How should we achieve that? What? Make what equal? So can I say it again? I'll do it one by one.
I can also say the mix probability of the bad chance to be delta. You will find this and at least how much you get the lower upper bound. You can find it at least the smallest example you need to get the smallest.
Yeah. So you mean you solve the equation that this chance is smaller than delta, or solve the equation that this upper bound is smaller than delta?
Upper bound.
Do you have the same idea as him, or?
Yeah, like set it up with inequality with delta, right? The function.
Yeah. I think you two agree. Yeah, I agree as well. So because I don't know the exact chance that this event happens. I only know the upper bound of this probability, right? So then, if I want to ensure the true probability less than delta, I can just solve the inequality that its upper bound is less than delta. Right? So if it is upper bound less than delta, then the true probability will for sure be less than delta. So then our problem becomes how to solve this inequality in terms of number of training examples. Any questions? Okay, no one feel confusing here, right? Okay, so now let us look at the inequality here. So we can take logarithm of both sides. So end up with logarithm of size of hypothesis space, right? Plus m times logarithm of 1 minus delta less than or equal to logarithm of delta, or 1 minus epsilon. So to simplify this question, we can further observe that e to the minus x, according to its Taylor expansion, is actually bigger than 1 minus x. So if you take logarithm of both sides, you end up with another inequality that logarithm of 1 minus epsilon is less than minus epsilon. So we can simply replace this term by minus epsilon, this upper bound, in this inequality, and to get a safer results for the number of training examples m. And then we have this new inequality, logarithm of size of hypothesis space h plus m times minus epsilon here, right? Because we just replace this one with minus epsilon, it's upper bound. And then we just move this term on the right hand side and this term on the left hand side, and flip the direction of the inequality. But now is m epsilon bigger than this. And then we divide both sides by epsilon. That's our result.
Is this taking into account that the n examples have a sufficient instance space to lead to a positive example? Because I can imagine you can have instances which are not informative, or perhaps your n examples don't have the right measurements. How does that fit into this?
Well, it doesn't explicitly reflect what I have said. So you can imagine that whether these examples are informative or contain contain large analysis are all expressed here. So yeah, you can imagine. Okay, the synergistic effect that we have a noisy training data give us upper bound of the chance that you end up with a bad hypothesis whose true error is bigger than epsilon. So what we want to address stress now is that, okay, we want to find out a guarantee that when how many examples, training examples we use, at least can ensure this chance to be smaller than a satisfactory level. Delta. And then to address this problem, we simply solve the inequality here. And then we solve the inequality and just build up another inequality. Remember, this one is actually for the upper bound of this one. So if you solve this inequality and this inequality must hold, and this inequality must hold, and it means the true probability of this bad event must be smaller than delta. That's the whole idea. Those are just inequalities, nothing else. So now, and when we reach this step, we say because epsilon is bigger than 0, right? Just divide both sides by epsilon, we'll end up with a lower bound of m. So basically says if m is bigger than 1 over epsilon, epsilon is the level for the generalization error, right? And times logarithm size of hypothetic space plus logarithm 1 over delta, then this inequality must hold, right? Equivalently, this inequality must hold. And what does this inequality hold mean? It just means the probability that we have this bad event happen is smaller than delta. So to summarize, our conclusion is that when m is bigger than this, then the probability we produce a consistent hypothesis, but true error is bigger than epsilon, is less than delta. That's the result, yeah. Anyone still feel uncomfortable about this? Okay, so we can equivalently to because it says, okay, when m is bigger than this, okay, and then the probability that we have a true error bigger than epsilon is less than delta. So equivalently, we can say, okay, the probability that we have true error less than epsilon is bigger than 1 minus delta. The same thing, right? The probability that we have a true error bigger than epsilon is less than delta is totally equivalent to we have a true error less than epsilon is bigger than 1 minus delta. So now we restate our conclusion in this way, which is consistent with the definition of path learning. So basically, it's like this. So we can conclude with probability at least 1 minus delta, high chance, right? A consistent hypothesis is we'll have a true error epsilon, true error less than epsilon if m is bigger than this m. This is the result we have derived so far.
Maybe I'm missing something, but we're talking about Occam's razor where you're trying to simplify your model.
Yes.
Basically, more simple models is better than a more complicated model. I'm kind of having a hard time tying that back to this. Is this so you don't just plug like 10 bazillion examples in, as you have like a number, like a quantifiable number as to which like a good value, a good number of examples is? Does that make sense? Like,
I think your question is good. This is what we want to discuss. How does this conclusion execute the Occam's razor? Yeah, that's something I'm going to discuss with you guys right now. Okay. So, but at least first you should know what does this conclusion mean, right? What does this conclusion says? So I want to make sure with you guys, everyone is good with this, right? And then let us look at what does this conclusion mean? Right? What can we find from observing this conclusion, from this result? So first, if you want to increase your generalization performance, right? If you want to your true error to be even smaller, what should we do according to this inequality? Suppose previously you set epsilon to be like 0.1. Now I want to set epsilon to be 0.01. What should we do to achieve this accuracy level with the guidance of this result just derived?
Plug in 0.01, get the correct n value, and use more samples.
Right? Because if you want to lower true error, right, that is a better generalization performance, this value is larger, right? That means you should increase the number of training examples. This is the first observation. If you expect a lower generalization error, what you should do? You should increase the number of training examples. Right? There is no free lunch. You have to supplement more. You have to give more to get better results. Does it make sense? Okay. So the second thing is about the term here. So you can say the second term is regarding the size of hypothesis space. So you can imagine where does you can think of what's the meaning of size of hypothesis space. The larger hypothesis space, the more complex the learning model, right? Because you make more assumptions. Your model is more complicated, and you have to search more. So actually, the size of hypothesis space indicates the complexity of the learning model or the learning algorithm. And now, from this, we can observe. Say to achieve the same level of accuracy and confidence level, epsilon and delta, if a learning algorithm chooses a larger hypothesis space, then how many training examples it will have? It will need a larger number of training examples as well, right? It is proportional to this bound. On the contrary, if the algorithm chooses a small hypothesis space, very simple hypothesis space, and then what will change in the size of training data to achieve the same accuracy level and confidence level? Excuse me?
Less data.
Yes, obviously, right? So you can say, when you increase the complexity of model, right, to obtain a good generalization performance, and with high confidence level, you have to use more training examples. And on the contrary, if your model is simple enough, and your model can still produce a consistent hypothesis space, then it will use just a smaller number of training examples. So this is where the Occam's razor reflects. Occam's razor favors a simpler model, meaning with a smaller size of hypothesis space. And third term, what does third term mean? Delta indicates the confidence level. Right? So the smaller the delta, the larger the confidence level. So now if I want to have a higher confidence level to achieve the same generalization performance, we also need to increase the number of training examples, right? Because when you decrease delta, you increase this bound. It makes sense as well, right? If you want to have a high confidence about generalization performance of your learned hypothesis, you better prepare more data, more training data. Okay, any questions about this? I saw your face that this is not that very fitting very well.
So all of these things affect how much samples we would need to collect. But just looking at the equation, it seems like the most significant term is our error expectation. Like if we wanted to half our error, that would correspond to we would need twice as many samples to achieve that. Whereas if we were to half our hypothesis space, that would only result in a smaller decrease. Like we would just be cutting that log in half.
Yeah, that's a very interesting observation, and yeah, but this is just a lower bound, so it is not equal. If it is equal, yeah, you're right. So the change rate, so the increase rate or decrease rate when you for different parameters might vary, right? But this is just the lower bound. So what we discussed so far is just qualitative, not quantitative. It's actually some kind of criticism about the computational learning theory is about they are based on all the analysis conclusions are mainly based on the bound. So if your bound is loose, then it cannot accurately reflect how the changes parameters can lead to the change of the interesting quantities like generation performance or sample complexity or even computational complexity. But this result is sufficient for you to understand some principles like Occam's razor, and also understand that if you want to increase the generation error with high confidence, you need to increase the number of training examples. But as to exactly how many examples you need, this bound cannot give you an accurate estimation. Any other questions? Okay. Yeah, this reflects Occam's razor because it expresses preferences toward small hypothesis space. But in general, complicated or in other words, larger hypothesis space does not necessarily mean it is bad. In fact, sometimes it's very good as long as you can provide a huge number of training examples. So this is actually consistent with our practice, especially like the example of deep neural nets, right? So everyone knows that deep neural net will consume a huge number of training examples, but if you fit into enough sufficient training examples, the prediction performance is amazing. But if you just like use 2 examples, 10 examples to train deep neural nets, that won't be good. So even with this very simplified theoretical model, but it can provide some practical guidelines when you conduct supervised learning tests. So let us consider some practical principles. So suppose we want to conduct the supervised learning test practice. We're not talking about toy examples. We're doing some real world tasks. And so now, giving you a sample of M training examples, according to what we have derived so far, we can first find out some hypothesis which is consistent with all training examples. Meaning that we're trying to fit these M training examples with a powerful model which ensure a 0 training error. And then to claim that our learned hypothesis has very good generalization performance, we can utilize theory we have just derived. How can we use that theory? We just check whether M is sufficiently large. If M is sufficiently large, we can like safely claim that or safely brag that our learned hypothesis is very good. Whatever it can be close to the target function in whatever cases. And how do we check that? We just use this inquiry. Right? So you can choose an arbitrary epsilon and delta, and check whether M is bigger than this. If M is bigger than this, you can conclude that, okay, my algorithm, my learned hypothesis, or my learned model will have the probability at least 1 minus delta to have the true predicted performance, the true error less than epsilon. So see the point? This is a way to examine your or give a conclusion or give a claim about the generalization performance of the learned model. Your question?
Could you give an example of a complex hypothesis space and a
So a simple hypothesis space. You can imagine if you want to do if you want to learn a function of Bloom variables, right? Your function is binary, and all your inputs are Bloom binary as well, right? So you have n binary features, and the output is binary. So what is a hypothesis space? Size of hypothesis space? 2. Suppose you have n Bloom features. 2 to the n, right? So it sounds very huge, but it's finite, right? That's one example. Another example, suppose you're learning algorithm, right? Just search for some continuous function, say just a linear function, and parameterized by some weight vectors. All those weight vectors are continuous values, right? So what is hypothesis space? What?
Size of the vector, basically.
Not size of vector. You can imagine. You can try to count how many distinct real vectors do you have. How many? Infinite, right? Because these are continuous values. You cannot enumerate all of them. So this is the case. But here, let's just assume, okay, our learning task is not that hard, and we can safely choose a finite hypothesis space. And then giving you a practical task, one strategy that you find out a hypothesis which is consistent with all the training examples. And then you test whether the number of training examples is bigger, satisfies some kind of include here with specific epsilon delta. Say epsilon is 0.1 and delta is 0.1. So if your number of training examples is bigger than this, then you can simply say, okay, with probability at least 1 minus 0.1, which is with a chance at least 0.9, the true error of my learned hypothesis is smaller than 0.1. So see, this is a way to claim the generalization performance of the learned hypothesis. Any questions? On the other hand, if I want to give some guarantee about learned hypothesis. Right? So say if I require that the confidence level is 0.01 and epsilon is 0.01, but you're free to choose whatever number of training examples you want. And what should we do? What should we do? An idea? I mean, suppose now I know my learner can always return a consistent hypothesis, right? Zero training error. And now I require you to give me a hypothesis which can reach the specified learning true error level and specified confidence level. And what should we do?
Find out calculate m.
Yes, exactly right. So just if you know the size of hypothesis space, you know your requirement for epsilon and delta, then just calculate this lower bound. You just pick up the number of training examples bigger than its lower bound. After the training, you can claim that, okay, my learned hypothesis has this true error epsilon with chance at least 1 minus delta. Right?
So back to hypothesis space. So determining the size of the hypothesis space is the number of possible distinct inputs and outputs. Does that make sense? So you said before with the Boolean, we're giving a simple example of Boolean where the output at Boolean values is 2 to the n. But like, what if the input isn't? What if the input values aren't necessarily
Binary?
Yeah.
Yeah, that's a good question. So if it is not binary, if it is continuous, then you cannot expect a finite hypothesis space, right?
So if it is infinite, then that falls apart, right? Yeah.
No, you cannot use it. So this just applies to like finite hypothesis space case. Any other question in this example?
If we relax consistent so that like it's allowed to have a very, very small error gamma or whatever, would this work for infinite cases in that case?
Yeah, that's a very good question. Yes, there is some kind of corresponding case for that. And in more realistic scenario, we cannot ensure that your learning algorithm can always find out inconsistent hypotheses. And in this case, how can we bound this error and get sample complexity? This is called agnostic learning. So you will give some bound, like what's the sample complexity, what's the lower bound of the sample complexity to ensure that the difference between the true error and the training error is less than some gap. That's how their theoretical results are described.
In that case, you could use, even if your hypothesis space is infinite, you would still be able to, to use a similar
Yes.
equation for that.
Yes. And when your hypothesis space is infinite, well, obviously this bound is meaningless at all, right? Because logarithm of infinite is still infinite, right? So it's not meaningful at all. So we must choose other type of metric to evaluate the model complexity. That metric is called VC dimension. VC dimension. And VC dimension is kind of a well-known measure to indicate the complexity of your classifier. And we'll introduce this concept when we discuss small vector machines. Any other questions? So actually, you guys ask a question. If you don't ask, I will ask. What if H is infinite? So this those examples does not apply at all. Right? All discussed later. So so these are all about the computational learning theory we'll cover in this semester, and we won't go to too many details about that. And the usage of computational learning theory is just give you a justification of theoretic guarantee about different types of learning algorithms. You are not required to like derive something based on those, but you're required to understand what is cap learnability and what does those lower bound of sample complexity mean. Right? What kind of insight can we get from those results? And later, when I present you some other lower bound about sample complexity or lower bound of the true error, you should be able to understand it. Does it make sense? Okay. So so now let us continue our specific learning algorithms. So we will start with another type of learning algorithms called ensemble learning. So so it is a kind of a general learning strategy rather than some specific learning algorithm. Although we will mainly focus on one famous learning algorithm called Ida boosting, right? And what is ensemble learning? So basically, ensemble learning is a machine learning implementation of the proverb, like two heads are better than one. And I would like to modify this proverb a little bit, like two crappy heads are better than one. That's the idea of ensemble learning. Two what? Two crappy heads. Two crabs are better than one. Does it make sense? Yeah. It sounds not that makes sense, but you will see that actually it is quite amazing, and there are many. They have very broad usage, very successful. This type of learning algorithm. So we'll introduce two ideas in ensemble learning. So one is called boosting, and the other is called bagging. And here's the outline. So we'll first introduce the concept of boosting, and you'll say why the learning theory is useful. I can tell you bagging boosting comes from research in computational learning theory. And then the theoretical results motivate machine learning researchers to develop a practical ensemble learning algorithm. It turns out to be very, very effective. And then we'll introduce the most successful and widely used algorithm called AdaBoost, and everybody should be able to implement your own AdaBoost. And then we'll introduce bagging method. And bagging method is even simpler, but surprisingly, works surprisingly well. So first, let us look at what is boosting. So basically, boosting is a general learning approach to construct a strong learner, a strong learning algorithm, given a collection of weak learners. So weak learners are the crappy learners. Refer to what I'm saying, crappy cats, crappy craps. So, but as we will say, that just simply combine a bunch of weak learners, you end up with a very strong classifier or predictor, which could be very accurate in practice. So the boosting algorithm is motivated by addressing a theoretical approach, a theoretical question in the packed learning. Right? That is published in this original paper by Professor Robert Shapiro. It's a very pioneering work. And this made him won the Gödel Prize in 2013, 2003, I forgot. It's kind of the Nobel Prize in computer science theory research. So boosting is practically very useful. And let me show you a few examples of its usage. Right? A very famous usage is the face detector. So whenever you use your cell phone or use digital cameras to take pictures, right? As long as there are some people inside the camera, you often find that their faces are bounded by those green box or blue boxes, right? And they're very accurate and very fast. So those algorithms, those functions are implemented by AdaBoost algorithm. So they're implemented in hardware, so it's very fast. So you can imagine how widely it's used. Another very successful application of boosting is handwritten letter recognition. I suppose you have a bunch of letters written by human beings. It's very messy. Can we still recover or identify which letters is which, right? So boosting turns out to be very effective for those tasks. And also task classification, tag news. The one machine learning task we introduced at the very beginning of our class, right? Information retrieval and motion capture, detect what kind of motions do you use? Like you wave your hand, like just turn around. It's very important in like 3D reconstruction and whatever, and DNA sequence analysis, and etc. So actually, boosting algorithms are very widely used, but people just do not realize it. So to introduce boosting, let us first make some formal problem setup. So from what we have discussed in computational learning theory, we know those effective and efficient learning algorithms can learn the particular type of concepts with high chance, with high prediction accuracy, with high generation performance, right? So we call this type of algorithm as a strong type algorithm. So definition of strong type algorithm is consistent with the definition of type learnability. So basically it says, okay, if the algorithm is strong, learning algorithm is strong, then for arbitrary data distribution and for arbitrary settings of the epsilon delta, and you only use polynomially many training examples to find a hypothesis with true error less than epsilon and with high chance, which is at least 1 minus delta. So this is called a strong pack algorithm. But in addition to the strong learning algorithm, we have also many other not very strong learning algorithms. We call it weak learners. So weak learners, we formally call it weak pack algorithm. So weak pack algorithm says that, okay, I can do the same thing as a strong pack algorithm, but you cannot set upper level of the generalization performance. Epsilon cannot be very close to 0. Instead, epsilon is only bigger than or equal to 0.5 minus some small value gamma. Say, epsilon could be bigger than 0.48. Epsilon could be bigger than like 0.4. But epsilon cannot be 0.001. If a learning algorithm uses polynomially many training examples, can only find out hypotheses with true error less than epsilon, such that epsilon is close to 0.5, we call it a weak pack algorithm.
What exactly is the gamma?
Gamma is just a small number. It's constant small number. But it's you mean the usage of gamma?
I'm wondering how small, like, does it have to be under 0.05, or is this a parameter?
Well, you can imagine it's kind of a constant, unknown constant, but it is close to 0. It's just some unknown constant such that when you analyze it, you can plug in gamma. But there is no explicit like way to quantify gamma. I can just tell you, okay, gamma is close to 0. Why I say gamma must be close to 0? Because it means this upper bound of the true error is close to 0.5. So what does it mean? You can only specify the upper bound epsilon close to 0.5. What does it mean? It actually means your learning algorithm, your weak learners, the generation performance of the true error is close to 0.5, or a little smaller than 0.5. In other words, your weak classifier, its performance is a little better than some random classifier. Do you get it? So random classifier means that, okay, I just toss a point, right? And then look at whether it is head. If it's head, then it's positive. Otherwise, it's not. So the generation performance of random classifier is 0.5, right? A weak classifier is just slightly better than random classifier. That's it. Does it make sense to everyone? That's the formal definition for that. So given the formal definition or rigorous definition of the weak, strong pack algorithm and weak pack algorithm, and the theoretical question would be, does weak learnability imply strong learnability? Meaning that if I have if you're free to build as many weak classifiers as you want, right? Can you smartly combine them or enhance them to be very accurate in predicting performance? That's what motivates the invention of boosting algorithm. So here's just a brief history of boosting. So it originates from the pioneer paper we just mentioned, right? So by Robert Shapiro, and he first proposed the first probable boosting algorithm, and called weak learner 3 times on 3 modified distributions, and got slightly increased in accuracy. And apply recursively. Obviously, this is not practical, but this is the first algorithm, so its research value is large, is big. And then Brown in 1990 proposed proved that optimal algorithm that boosts by majority, and that this is actually referred to what we will discuss later in this topic is about bagging algorithm. And in 1992, those three researchers experiments early boosting algorithm and showed that actually in practice they have many drawbacks. It's not practical at all. But then later in 1995, data boost algorithm was invented, and it shows very strong practical advantages. And following that, numerous papers and applications were stimulated. And those two guys won Godel Prize in 2003. Okay, this is a brief history of boosting algorithm. And our primary focus is on this most successful and widely used algorithm, data boost. So we'll introduce what is the intuition of data boost and algorithm details, and we'll discuss a little bit why does it work. So it's kind of interesting that you say data boost always overfit training data, but it does not affect its generalization performance. And even better, you see that even when the training error goes down to 0, the true error can still decrease. That's amazing. So it's kind of an open question like 10 years ago. People trying to find out a more appropriate theory to explain this phenomenon. And there is some theory try to understand it's called max margin. It's called margin bound, which is tighter than the bound, the kind of bound we have just discussed. Right? But we won't cover it in detail. Right? So to illustrate the intuition of the boosting algorithm, let us start with a toy example. So suppose we have like 10 training examples, right? And located in this rectangular, we have five positive examples and 5 negative examples. Now, we have a weight classifier. So how we can this? The classifier can only express as axis parallel lines. So either parallel to the x-axis or parallel to y-axis. So you can imagine this is very weak, right? So it only works when like positive examples, negative examples are both aligned along some axis, right? If the classification boundary is kind of like this, it won't work because you either your line, the classification boundary is like this or like this, right? You cannot deal with this case. So we want to invest the weight by just simply combine those weight classifiers to increase the prediction accuracy or generalization performance. How can we do that? We first consider all training examples as equally important and simply train a best classifier on this data, although it is best, but the prediction performance is not satisfactory at all. You say it wrongly predict 3 positive examples, right? And clearly, the training error is 0.3 because we have 3 positive examples which are mistakenly corrected out of 10 examples in total. So the error 1 in the first one, epsilon 1 is 0.3. And we denote the classifier in the first round by H1. Now, to carry out next round, we increase the importance of those wrongly predicted examples. And at the same time, for those correctly predicted examples, we downweight them. That means we have a set of weights for all the training examples, right? 1 for each example. So for round T, we have the set of weights dt. So if in the previous round, a training example is correctly predicted by the learning classifier, then the weight is decreased in the next round. If an example is correctly predicted, is wrongly predicted, then we increase the weight. So why should we do that? The motivation is that when I try another classifier, I do not want to make the same mistake. I want to overcome this mistake. I want to correct the mistake made by previous learners. And for those examples which have already been correctly identified by the previous learners, it is not that important to the current learner. So I downweight their importance. That's the idea. So now let us look at, in the second round, right? We learn a classifier on those weighted training examples, right? The set of weights are D2, because it's round 2. And we'll end up with another classifier we denote it by like H2. But unfortunately, although obviously by increased importance of the 3 positive examples, we avoid misclassify them again, right? But we bring in new wrong predictions, these 3 negative examples. And we can compute the weighted error is 0.21. So why it is not 0.3? What?
We change the weights on the plus.
Yeah, exactly, right? Because we do not, right now, from round 2, we do not consider each training example equally important, right? We change the weights. So for those 3 negative examples, their weights are decreased because they're correctly classified by the classifier in the first round. So correspondingly, if they are wrongly corrected by H2, then the training error is smaller than 0.3. So in general, we can define the weighted error in this way. So it is 1/2 minus 1/2 times this. It's a summation between the products of the sample weight multiplying with the true label yi and the prediction of the classifier hxi. That's how we calculate the weighted error in each round. And to see why it is reasonable, we consider 2 cases. First, when your prediction is wrong, meaning that hx is not equal to y, right? Then what is the product between yi and hxi? What is the product? So if yi is 1, your prediction is wrong, then what is hxi?
0.
Minus 1. Don't use 0. We assume positive 1 and negative 1 here. So it's minus 1. So the product is minus 1, right? When yi is minus 1, if you have a wrong prediction, then your prediction must be positive 1, right? So the product is minus 1. So whenever you make a mistake, the product between the true label and the predicted label is just minus 1. And similarly, not similarly, in another case, when your prediction is correct, then what is the product? Just 1, right? Either you both are 1 or you both are minus 1, right? 2 negatives are positive. So now we can consider like 2 extreme cases. So first, if your classifier is good enough to have 0 training error, to correctly predict all the training examples, then what will be the epsilon t? 0, right? Because if your classifier can correctly predict every training examples, then in each summon, yi times hxi must be 1, right? Because they're correctly predicted. So, and now it becomes a 1/2 minus 1/2 over the summation of the sample weights. So the summation over all the sample weights is simply 1. So epsilon t is 0. So this is reasonable, right? So now, what if your classifier is so bad that it wrongly predicts every training example? What is epsilon t here? 1, right? So now, if you can do further some simple mathematical derivation, you find that equivalently, epsilon t is simply the summation of the weights for those incorrectly predicted examples. So I will leave you an exercise as access to prove that these two definitions are exactly the same. So imagine that if you have like equal weights for all the training examples, then DTI is simply 1 over m. M is number of training examples, right? So in that case, then epsilon t is simply the training error, the standard training error we have. That is the number of the incorrect predicted examples over the total number of training examples. But now, if you have different weights for training examples, then each error only contributes to the extent, whatever it is important, right? It could vary. That's why we have like 0.21 here, because they have different. The three negative examples have different sample weights. So that's how we define weighted error here. And now, again, after the second round, we have three incorrect predicted examples. We downweight, or we increase the weight for those wrongly predicted examples, and downweight those incorrect predicted examples by H2. And then we have D3, right? And on those newly set of sample weights, we train a third classifier in the round 3, H3, right? It's here. And obviously, we still have some wrong prediction on the training data. Here, here, and here.
Do you ever get in a situation where you're just like toggling between like increasing the weight and decreasing the weight?
Yeah, of course, there could be some fluctuations. Yeah, obviously there could be. But it doesn't matter. It doesn't matter. It doesn't affect the conclusion we have. We'll have. And now, because of different setting of the sample weights, right? So although you have 3 mistakenly classified examples, your weighted error turns out to be 0.14. So now, suppose we stop now. We only run 3 rounds. 3 rounds, and we end up with 3 weight classifiers. Right? So to integrate those weight classifiers, I just do a linear combination of their predictions. That is, the final prediction is simply alpha 1 times the prediction of H1, alpha 2 times prediction of alpha 2, plus alpha 3 times prediction of H3. We integrate all the predictions. So we can say alpha values like alpha 1, alpha 2, alpha 3 are just the rows for each weight classifier in the boosting algorithm. That's the whole idea.
Is the addition specific to what classifier you use? Because I can't really see an obvious H1 plus H2.
You can imagine, like, if I want to test a new example X, right? So I have a prediction by H1, which is H1X, and prediction by H2, H2X, prediction by H3, H3X, and then just do a weighted combination of their outputs. So this output could be 1, this could be -1, this could be 1 as well, right? So you end up with alpha 1 minus alpha 2 plus alpha 3, right? And then you can see whether it's positive or negative. If positive, then the final prediction will be positive.
Okay, so like if I'm looking at like say the bottom right corner, that negative, considering something in that corner, I would take the combination prediction, say like it's most likely positive. In this case negative.
Most likely positive.
For a specific thing, but like there isn't an image that looks like all 3 of them together.
So according to which prediction is more important, it is reflected to those alpha values, the voltage values. But prediction, when you use prediction H1, H2, H3, just use them equally. Okay. Yeah, so this is a general outline of boosting. So let us discuss the details on Monday.
I was like, oh, yes.
And to pass this, this is later.
Oh.